Hello everyone, welcome to my YouTube channel. So today I'm going to discuss an interesting problem from linear algebra. So this is the question from IIT Palakkad PhD entrance test. Okay, someone sent me this question, so I'm thinking that this is a nice problem. So I also want to share with you this solution. Okay, so the question says that let F be a subspace of a vector space Rd. That means F is a subspace of a vector space Rd. That means d-dimensional real vector space. Okay, Rd. And suppose F contains a vector all of whose components are positive. That means suppose there is a vector V in F such that if I write V as V1, V2, say Vd, because this is an element of Rd, then all Vi is greater than 0. Okay. Then show that F is spanned by its probability vectors. Okay. What is the meaning of probability vectors? Probability vector means a vector is called probability vector. Okay, all of whose components are non-negative and sum is 1. That means say x is a probability vector if and only if I write x as say x1, x2 up to xd here, then all xi greater equal to 0 and summation xi I equal to 1 to d is 1. Okay, so this is the meaning of probability vectors. So the question says that if F is a subspace that has at least one vector all of whose components are positive, then we need to show that F is spanned by its probability vectors. Okay, so how do I approach this problem? So let's first assume that a dimension of F is 1. Okay, so let's see what is happening in case of one dimensional space. Let's assume dimension of F is 1, and we already from the given condition we already know there exists a vector V such that all Vi's are positive. Okay, now consider this vector V tilde equal to V by summation of Vi I equal to 1 to d. Okay, this sum makes sense because Vi strictly greater than 0. That means Vi summation Vi I equal to 1 to d. This is strictly greater than 0, right? So that means V by summation I equal to 1 to d Vi, this is the vector, right? This is the vector, and V tilde also belongs to F, as V tilde is a scalar multiple of V, and V is already in F. That means any of its scalar multiple also in F, right? Because F is a subspace, right? And since dimension F is 1 and V tilde is a non-zero vector, that means F is span of this V tilde. Okay, that means our claim is proved. The question is proved in case of when F has dimension 1, that F can be spanned by a probability vector. Why V tilde is a probability vector? Because if you see, you can see, right, V tilde is probability vector because Vi tilde means it is Vi by summation Vi I equal to 1 to d. If you sum Vi tilde, then you will do Vi I equal to 1 to d by summation vi I equal to 1 to t, which is 1. That means v tilde is a probability vector, right? So that means in case of dimension 1 we can prove it. Now what will be our obvious choice? Our obvious choice will be induction hypothesis, right? So how can we use induction hypothesis? So dimension of f can be at most d, because since it is subspace of Rd, right? So let's assume dimension of f is k, which is let equal to d. Okay, and by induction hypothesis this is assume the claim is proved for dimension of f less equal to k minus 1. So we have already shown for k equal to 1, right? And if for dimension k equal to 1 we have already proved, and we assume that it is true for k minus 1 up to k minus 1. So now we need to show when dimension of f is k, right? Okay. Okay. So by given condition there exists a vector v belongs to f such that vi is positive, right? Now choose a k minus 1 dimensional subspace such that subspace set w such that w is span of w1 w2 up to wk minus 1 such that w1 equal to v, this v. Okay, I can choose that because take v then extend it. Okay, extend it and choose some k minus 1 vector which are linearly independent, that you can do, and then take the subspace spanned by that vector. Okay, then w is a k minus 1 dimensional subspace, and w contains a vector small v having all the coordinates, all the components positive, right? That means by hypothesis w is spanned by its probability vectors, so I can write w is span of say t1 t2 up to tk minus 1 such that ti is a probability vector, right? Okay, now f is k dimensional subspace, w is k minus 1 dimensional subspace inside f. Now choose a vector x belongs to f minus w. Okay, clearly w not equal to f, right? Because f has dimension k and w has dimension k minus 1. So choose a vector x belongs to f minus w where x equal to x1 x2 up to xt such that summation xi I equal to 1 to d is non-zero. Okay, choose a vector such that this happens. So it is very important part, this proof. So choose a vector x from f minus w such that summation xi I equal to 1 to d. This is non-zero. Now question is why such a vector exists. Question, why such a vector exists. Right? Question is why such a vector exists. Okay. So if not, there doesn't exist any vector such that this happens. That means for all u belongs to f minus w, summation ui I equal to 1 to d is 0. Right? Now consider the vector. So first choose any u belongs to f minus w. By our assumption, summation ui I equal to 1 to d is 0, right? Then consider this vector x, t1 plus t2 plus tk minus 1 plus u. Right? This is not in w, right? But this is in v. Sorry, this is in f, because t1 is f, t2 is in f, tk minus 1 is f, u is in f, so their sum is also in f. But this is not in w, because if this is in w, that means x minus t1 plus t2 up to tk minus 1 belongs to w implies u belongs to w, which is a contradiction, because by our assumption we assume u belongs to outside of f minus w. Right? Now see, that means x belongs to f minus w. That means x belongs to f minus w. Okay. So x1 equal to t11 plus t21 plus tk minus 1 plus u1. In this way, xt equal to t1d plus t2d plus tk minus 1d plus ud. That means summation xi I equal to 1 to d is same as summation ti I equal to 1 to d plus summation t1y summation I equal to 1 to d t2y plus so on summation I equal to 1 to d ui. Right? By our assumption, this is 0. This is 0. And since ti is a probability vector, so these all are 1. Right? That means summation xi I equal to 1 to d is k minus 1. Right? Which is clearly non-zero. Because k is definitely not equal to 1. Because if k equal to 1, then we have already proved it. So there is nothing to show. So we assume the dimension of f is at least 2. That means k not equal to 1. That means summation xi I equal to 1 to d equal to k minus 1, which is non-zero. Hence this gives a contradiction. This gives a contradiction. Right? This gives a contradiction. Right? So why this gives a contradiction? Because first we already assumes that for every u belongs to f minus w, summation ui I equal to 1 to d is 0. But if we assume that, then we get a vector in f minus w such that summation xi I equal to 1 to d is non-zero. Right? Now you are done. Now I leave it to you to find a vector from f minus w such that which is a probability vector, okay, or should I tell that? Okay, let's tell that. So you have already shown that there is some x such that summation xi I equal to 1 to d is non-zero, right? Then take x tilde equal to x by summation I equal to 1 to d xi. Then x tilde belongs to f minus w, right? Because x tilde belongs to f, as x belongs to f, and if x tilde belongs to w, that means its scalar multiple x also belongs to w, which is a contradiction. That means x tilde belongs to f minus w, right? And this is also a probability vector, and x tilde is also a probability vector. So a probability vector. Then f is span of t1, t2, tk minus 1 times x tilde, comma x tilde, right? Dimension of f is k. We are done. So this is actually a nice problem, but easy problem, but you have to think it properly. Okay, thank you. I hope you find it beautiful.